Hello, my name is Yun, and first of all, many thanks again to the challenge organizers, Eero, Tao, and everybody for this challenge. And we definitely learned a lot by doing this challenge, so it was a very good experience. Today, I'm honored to talk about our approach in tackling this challenge, and this is joint work with Hyungtae Lim, Jingnan Shi, Lucas Schmidt, and Luca Carloni. And I especially want to acknowledge Hyungtae, who is not here physically today, but he was the main driving force behind the success of this project. Yep, so this is our final score, and as I think you already showed this, the criteria in this challenge. And here are some qualitative results that we have. So the light green scans here are the known, the given scans, and the colored ones are what we're trying to predict and estimate on the competitor's side. So let me dive more into the details. So I'll first give a quick overview of the preliminaries and goals of NSS challenge to set a stage of what we had to work with. Next, I will highlight the difficulties of the challenge, which will kind of inform some of our design decisions. And then I will talk about our solution and pipeline based on some prior work from Spark on all-layer robust classical perception methods. And finally, I will finish with some more detailed discussion on our results. So just want to take a step back and understand three terms: area, stage, and scene. So area, in spatial temporal terms, you can kind of think about area as where a scan was captured, so more on the spatial side. And in terms of stage, it's more on the temporal side, when a scan was captured. And sort of the scene is the position of the world based on the collection of scans taken at various times or various areas and stages. The setup is also similar to postgraph SLAM. Each node of the postgraph corresponds to a scan, and edges denote relative transforms between two nodes. So here we visualize the nodes in the scene with different colors and also show example formats given nodes and edges. Nodes are given an ID and edges are directed with a source and target node. The transforms of the nodes and edges are given for the chaining and validation set, but we have to predict the ones for the test set. Yeah, so the goal is to fill in these transformation matrices. So those will be relative for the edges and global for the nodes. And that's the main goal of the challenge. Why is it difficult? Well, so for one thing, temporal changes makes the registration very difficult, and it's not very straightforward to register point clouds together with changing artifacts. And then second, sometimes scans can be degenerate or lacking in feature, making it very difficult to find correct transformations between the registrations. And lastly, scans of the same area could be captured with a different perspective. For example, one scan could be captured within the room, and another scan could be captured in the hallway outside the room. That makes it so that means there's very limited overlap in features to register the scans together. So we simplify the complicated dynamic multi-way registration problem into a two-step approach for robust localization and mapping. And it sort of recalls some resemblance to a classical SLAM system in the sense that we have a front end that does the registration and also a back end that does like this iterative map optimization framework. The first step, which is similar to a front end, is an outlier robust registration module that first computes FPFH features. They're relying on Robin and Quarto for outlier rejection and robust registration. I'll go into this in more detail now. So it's a completely learning-free pipeline. After we first extract FPFH features from a pair of point clouds and perform matching, Robin is used for outlier rejection by pruning the outliers, and Quattro is used to perform registration and obtain the post estimates. So more about Robin. Robin is a graph theoretic approach to reject outliers in robust estimation problems produced by Jingnan Shi from our lab. It uses invariance to check compatibility among subsets of measurements and create a compatibility graph. And Robin then rejects outliers by computing a max click on the compatibility graph. In our case, we use a point with normal compatibility test because this is an indoor environment. So this checks that the distance between points and also the angle between point normals are invariant under rigid transformation. After rejecting outliers, we pass this into Quattro, which is a 4 degree of freedom outlier robust point cloud registration approach that estimates X, Y, Z, and yaw using graduated non-convexity to solve this truncated least square cost function. And it's also have some robustness against outliers. And I think the main key characteristic of our pipeline is that we have this ability to validate the output of a scan-to-scan registration, because Quattro is able to give us the number of final inliers in the registration. So for the purpose of this challenge in particular, we set a minimum required number of valid inliers to be 5, meaning that if you have more than or equal to this number of inliers, it's a valid registration, and if not, it's a invalid registration. Moving on to the second step, more of the backend map optimization framework. What we want to do is we want to utilize the ground truth poses given for some of the nodes. So this can give us some partial information that will act as a median or initialization before performing more robust optimization. So what we do is we create this database that consists of partial scene constructed using the training and validation data was given ground truth poses by accumulating the scans. And using this partially constructed map, we then sample a map at the known node poses that were given in the test or in the training and validation set to augment the scans of the known nodes. So this allows us to better handle the degenerate scans and difference in perspective by having denser and wider coverage scans from each known node. Next, we have 3 different types of edges that we categorize all edges into. So we have the known to known based on edges connecting given nodes. We have the known to the unknown, and then we have the hardest ones, the unknown to the unknown. And these are what we have to eventually estimate. So for each unknown node, we can perform pairwise registration with each neighbor in the same stage using Quattro in a coarse-defined manner. So this will give us a lot of poses from the known nodes in the stage to the particular unknown node. And utilizing this valid registration results, we utilize a trick used for multi-robot initial alignment from Chimera Multi in a previous paper from lab, and perform robust post-averaging on the change measurements of a different path. So basically, you can imagine we have an anchor node, and you have multiple paths to get to the unknown node. Each of it has a slightly different registration result due to noise and outliers. But we can perform a robust averaging operation that gives us an optimal guess on what that poses. Meanwhile, for the unknown and unknown scan registrations, we also perform pairwise registration, and based on the validity check, we are able to check if two nodes are registered correctly to each other. And if they are, we can combine the 2 scans, so we can keep growing this the scan accumulation for the unknown nodes, giving us more features to work with. And just to summarize, this is like a very iterative process. So I want to show it in a summary here. So here's a quick example. So we have this graph that we start with the green known nodes and edges. And also what we want to do is we want to find the poses of the unknown nodes shown as the white circles, and also the transforms between the unknown red edges. We perform pairwise registration using Robin and Quattro, and based on the validity of the registration, we update both the state and the nodes via robust post-averaging, as I mentioned before, while also accumulating the scans at each node and the scan of its neighbors. And we can sort of keep doing this and continue the iteration until all the poses of the unknown nodes are updated. All right, let's look at some results. So this is a case where we have 6 known to unknown nodes edges and none unknown to unknown edges, which is the easiest case for our pipeline. And we're able to achieve centimeter accuracy in this approximately 40 meter by 20 meter scene. And this is a similar case where there's no unknown to unknown edges, slightly bigger, 70 meter at 30 meter, and we also get very good accuracy. This scene has some unknown to unknown edges that are degenerate, but with a few iterations, we're able to recover a good result. And kind of jumping forward to one of the most challenging cases for us, which is this case where we were not given any known edges in this particular scene, but we were still able to get a low global RMSE of 0.032, largely due to this scam merging, scam accumulation scheme that we were using. And then this is, I think, the largest scene in or scenario in the data set. This is our worst result. While there's like tens of unknown edges and there's 161 known to unknown edges and 11 unknown to unknown edge, we still achieve a pretty good RMSE, less than a meter for this 50-meter by 50-meter scene. But definitely our pipeline definitely struggles a bit more in this case, since the number of unknown nodes increased. And here's a summary of our results. So that's a quick overview of our pipeline, and we look forward to testing on more difficult data sets. And we also look forward into investigating this approach more in different contexts, such as large-scale SLAM or multi-robot, multi-session SLAM. And yep, so to conclude, we mostly tackle the NSS challenge using classical outlier robust perception methods. And in these data sets, we're able to achieve pretty good results. And we also learn a lot from what we can do with these just classical outlier robust methods. Thank you very much. One question, if anyone has any questions about your results. Do you plan implementing in outdoor very at the moment it's purely indoor? So our method can easily be generalized outdoor. I think the only part that's specifically to indoor right now is well, actually two parts. One is the outlier rejection, where we're doing the point to point and point to normal. If we want to do it outdoor, we can only do point to point, right? Because normals probably will be harder to enforce in that sense. And the other is the robust registration, Quattro. Now that one's 4 degree of freedom registration. So in outdoor scenarios, we probably want to do 6 degree of freedom, which we do have, but definitely will be a more challenging scenario. And we're also curious in trying that out, but we haven't yet. Thank you.